All right, let's jump right in. Today, we are tackling a concept that is just so crucial for trigonometry, coterminal angles. And we're going to be doing it in radians. I'm telling you, if you can nail this down, a whole bunch of other trig concepts are going to click into place. So let's get to it.
And to get our heads wrapped around this, we're not going to start with some crazy formula. Nope, we're going to start with a simple little puzzle. So just picture a regular old-school clock on the wall. The hour hand starts up at 12. Now imagine it goes around for 13 full hours. Where is it pointing at the end of all that?
It's pointing at the 1. Think about it. After 12 hours, it's right back where it started. So that 13th hour just moves it to the 1. Even though it traveled way longer, its final position is exactly the same as it was at 1 o'clock. Remember that idea, a different journey but the same destination? It's everything.
So, that little clock thing we just did? Well, in math, that phenomenon has a name. We call it the coterminal concept. And all this really means is that it doesn't matter how many times you spin around the circle, if two different angles end up stopping in the exact same spot, they're coterminal. Simple as that. The path can be way different, but the endpoint is identical. Okay, so how do we actually find these angles when we're working with radians? Well, it turns out there's one super simple rule that governs the whole thing. That's it. That's the rule. You just add or subtract 2 pi. So why 2 pi? Well, remember, 2 pi radians is 1 full revolution around the circle. So adding 2 pi is just like our clock hand going forward 1 full spin. And subtracting 2 pi is like spinning it backwards 1 full spin. Either way, you land in the exact same spot. Now, here is the #1 pro tip for getting these right. You can't just add 2 pi to a fraction, like pi 6, without a common denominator, right? So the trick, every single time, is to rewrite 2 pi so it has the same denominator as your angle. This one little step, I promise you, will prevent almost every common mistake. Okay, enough with the theory. It's time to see how this works in practice. Let's do a few examples, and we'll start off easy and then ramp it up. All right, let's kick things off with a basic one. We've got the angle pi over 6, and our mission is to find another positive angle that stops at the same place. Since we want a positive angle, the easiest thing to do is just add 1 full rotation. So we add 2 pi. And here comes our trick. What's 2 pi with a denominator of 6? It's 12 pi over 6. See how easy that is now? The fractions match and we can just add them. And boom, there's our answer, 13 pi over 6. What this means is that if you go all the way around the circle once and then go an extra pi over 6, you land in the exact same spot as if you had just gone pi over 6 to begin with. They're coterminal. Okay, let's step it up a notch. This time we're starting with a negative angle, negative pi over 3. And the goal is a little more specific. We have to find the coterminal angle that falls in that first positive rotation, somewhere between 0 and 2 pi. So think about it. We're starting in negative territory. To get into the positive, we need to spin it forward. So we're going to add 2 pi. Using our denominator trick again, 2 pi becomes 6 pi over 3. Now it's just a simple addition problem. And we get 5 pi over 3. Now let's check. Is it positive? Yep. Is it between 0 and 2 pi? You bet. So that's our answer. This means that going clockwise by pi over 3 lands you in the exact same spot as going counterclockwise by 5 pi over 3. All right, time for a trickier one. Look at this. 19 pi over 4. This number is clearly much bigger than 2 pi, which means our angle has gone around the circle more than once. Our job is to basically unwind it until we find its simplest form, the one between 0 and 2 pi. Okay, since the angle's too big, our strategy is to subtract full rotations until we fall into that 0 to 2 pi range. A full rotation, 2 pi, is just 8 pi over 4 with our common denominator. So we subtract it once, we get 11 pi over 4. That's still bigger than 8 pi over 4, so it's still too big. We have to go again. And there we go, 3 pi over 4. That's our answer. So what we've just figured out is that the angle 19 pi over 4 is really just 2 full spins around the circle with an extra 3 pi over 4 added on to get to its final spot. So now that you've got the hang of how to do it right, let's talk about the 2 most common ways people get this wrong. Because if you know the traps, you can step right over them. And here's trap #1, the big one, mixing units. You absolutely cannot do this. If your problem is in radians, you must use 2 pi. If it's in degrees, you use 360. Trying to add 360 to a radian angle is like trying to add dollars and euros without converting first. The result just doesn't make any sense. So let's just hammer this home. Mistake number 1, mixing your units. Don't do it. And mistake number 2, which is easily the most frequent little math error, is forgetting that common denominator trick. It's a small detail, but it makes all the difference. Okay, let's zoom out for a second. We've been really focused on the how, but let's talk about the why. Why does this one idea, coterminal angles, actually matter so much in the grand scheme of trig? And this, right here, is the big reveal. This whole idea, this concept that you can spin around and keep landing in the same place, has a name. It's called periodicity. It's the reason the graphs of sine and cosine look like those beautiful, endless waves. Every 2 pi, the entire pattern starts over again, and again, and again. And it all comes back to this one simple idea. So, I'll leave you with this to think about. Now that you know for a fact that the values of an angle must repeat every 2 pi, what does that force the graphs of sine and cosine to look like? Think about that repeating wave and you'll see the connection. Thanks for joining me.